pleasure to introduce Sir Pascal Poupart. I'm going to claim Pascal as one of us, as he did his undergraduate at Gill and his master's degree here in the ancient days before electricity and, I mean,
no, not that
long ago. And then I guess a PhD in Toronto. As you can see right here, it makes it very easy. Pascal is a professor at McGill Waterloo, excuse me, and the C4AI chair, associate inspector. He's a prolific author, does a bunch of stuff in RL and a bunch of stuff all over the place, and is exceedingly well known for being probably the nicest person in the field. So it's funny to have the two of us contrasting in this respect. But you'll see what nice is really like. Thank you very much. Take it away, and we all we should be interactive as always. But there is a job talk afterwards. We've been told that we need to be sharp at around 10:50-ish. So help Pascal get through, but we should be interactive just the same. Okay, thank you very much.
Thank you. Yes, it's a great pleasure to be back. And I guess I still remember when I took my first reinforcement learning course with David many years ago. And then I guess today I'll be talking about reinforcement learning. So I guess the credit goes to David for introducing me to the field. Okay, so I do work on a number of things, and I do have as well a good number of industrial collaborators. So with my research lab, what we do is that I try to tie the two ends. So we get from industrial partners real problems with data, funding, and so on. And then we work on fundamental problems, publish them into top-tier venues, and then over the years, I've had a chance to collaborate with many good companies. Today, I would say about 2/3 of my research group works in machine learning. That is mostly, in fact, in reinforcement learning. But then I also have about 1/3 of my group doing work in natural language processing, and then I've got some other applications as well. Okay, so I'll be talking mostly today about one topic in the context of reinforcement learning. This is what I would call inverse constraint learning, so I'll define this in a moment. Then there's a second topic if there's time, but we'll have to see because we have to vacate the room quickly at the end. So if there is time, I will also talk about uncertainty quantification for risk-averse R. Okay, so a bit of motivation. So to consider the problem of autonomous driving, there might be various objectives. There's also some constraints, and some of these things are easy to specify. Some other things are harder to specify. And what has become a dominant approach is to essentially try to learn the objectives and also the constraints from demonstrations by experts, in other words, human drivers. Now, in this talk, I'll talk mostly about how we can learn constraints from expert demonstrations, but just to set the stage, let me just quickly review, I guess, how we formulate the problem, starting with what reinforcement learning is. Okay, so reinforcement learning is just this general problem where you have an objective in the form of a reward function, and then you try to optimize those rewards, maximize the rewards by obtaining an optimal policy pi star. Okay, now in many problems, if we want to ensure safety, or if there are, I guess, additional objectives that we don't necessarily want to optimize, but we want to make sure that we satisfy certain thresholds, then it makes sense to consider constraints. And then so there's a version of reinforcement learning known as constraint reinforcement learning, where we take as input rewards, a constraint or several constraint functions, and then we try to find a policy that effectively optimizes this objective here. Okay, so we maximize expected rewards subject to some expectation of cost being less than or equal to some threshold beta. Okay, this is all good in terms of doing control, coming up with a policy, but in this talk again, I will look at the inverse problem. So inverse RL is when we have access to the optimal policy, perhaps through demonstrations from experts. So here, D, just think of this as the data that comes from expert demonstrations. And then what we'd like to do is recover the reward function that the expert was optimizing. and that we can't observe, but this is what we would like to essentially infer. And the idea is that now if we're developing some system that should optimize some reward function, then perhaps we can simply pass on that reward function to our automated system. Okay, now when we've got constraints, then I guess it would make sense to not just infer the objective, the rewards, but also infer the constraints. So we've got a similar problem here. So we observe some expert demonstrations, then we recover both the rewards and the constraints. And then, so this is really like the inverse of this constraint reinforcement learning problem. Now, this is very general, and it is very challenging in the sense that there's some unidentifiability problem where some types of behaviors can be explained by maximizing some rewards, or could also be explained by satisfying some constraints. And it's not always clear what is needed. So in this talk, in fact, I'm going to focus on a simplified version of the problem where let's say that we have the rewards, so we know the main objective already, we have expert demonstrations, but what we're missing are the constraints. Okay, so we're only going to focus on learning the constraint. And this came, in fact, from our industry partner in autonomous driving. They basically told us, we know how to specify the rewards, the objective, that's all good. But when it comes to safety, when it comes to smoothness of the ride, comfort, and so on, then here there are behaviors that human drivers tend to follow. And we believe these things are best represented as constraints, and we would like you to learn constraints from the data. Okay, so that's the setup. And are there any questions regarding this? Good.
So are these, will these be completely hard constraints, or you could imagine, you know, the in-between case where it's kind of a soft constraint followed by a hard constraint. So
okay, so yeah, that's a great question. And then okay, we'll get to this in a moment. We're going to look, in fact, at soft constraints, generally speaking, because when you're learning things from data, especially for autonomous driving, let's say you want to learn the constraint of like, what's the gap that you should leave to the car in front, and you gather plenty of data, you will eventually see some examples of human drivers who actually had almost an accident but did not. And if you're trying to learn a hard constraint, the only interesting constraint you would learn is that the gap should be 0, because somebody will be arbitrarily close, right? And that's not good, right? So then we have to assume that our experts essentially will violate whatever constraint they're presumably trying to follow, and therefore it should be soft. Yeah. Okay, so let me illustrate now with a little cartoon the algorithms that we're going to develop, and then so it's going to be very simple for now. But then we're going to see how we can make these things realistic in a few slides. But I guess, okay, in this example, let's say that we have an agent that starts here, it's trying to reach a goal location right here. And let's say that we penalize the agent with a reward of -1 at every step. So in other words, it's really just trying to find the shortest path from a start state to a goal state. Now, let's say that on top of that, we have 2 expert demonstrations. So the first one starts here, goes around, it comes down here. The second one starts here, comes down, and also reaches the goal, okay? So this is what we've got. So now, if we know the reward function, again, let's say -1 for every step. So we could plan and let's say come up with a trajectory according to an optimal policy, ignoring any constraint. And this would give us the following shortest path, right? The trouble is that when you look at this shortest path, it is clearly different from the expert demonstrations. And intuitively, here we can conclude that this must be because there was a constraint that prevented the experts from just going straight down, and they had to go around maybe some obstacle or some parts of the state space that is considered infeasible. So if that's the case, then we can hypothesize where a constraint might be in this setup. And really, I guess there's only this cell that is traversed by our shortest path, but is not traversed by the other expert trajectories. So let's assume that this cell must have been considered infeasible, that there's a constraint that, you know, makes it infeasible. So then, given that, now we can optimize again our policy, come up with a new shortest path. Perhaps we get this one. Again, it's not the same as the expert trajectory, so there must have been a constraint, and then we infer that perhaps this cell again must be infeasible. And then we can keep on going like this, and eventually we arrive at some trajectory that is similar to the expert trajectories, and then we can stop and assume that we have a constraint that perhaps corresponds to what the experts must have followed. Okay, so that's the intuition, and then I'll show you some algorithm that will do this. Obviously, it's something way more interesting than just a little grid world, but with real data from autonomous driving. But before I move on, any questions regarding this intuition? Yeah.
So the expert demonstrations, they might not have any explicit reward for diversity. How do you tell in this case that the risks untouched are because of their constraints, or they're just being suboptimal or simply out of distribution?
Yeah, okay, that's a great question. So indeed here, I inferred that there must be a constraint for those cells because they were not being traversed. But you could imagine that, let's say that my grid world was way bigger, and then there were like additional cells around that were not traversed. Then does that mean that there are constraints there too, right? And here, I guess this is where the problem is underdetermined. But I guess what the assumption we're making is that the experts are optimal, and then if there's some paths that would go into a different part of the space, but would lead to a suboptimal solution, suboptimal policy, in other words, less rewards than the paths that we observe from the expert, then it's normal that they just wouldn't consider those, and we don't need to infer any constraint for that part of the state space because it's suboptimal. Okay, so that's the assumption that we're making here.
If there are 100 steps between that they didn't go in, which of the 100 steps do you blame? Because they could have been any one of those could have been blocked.
Yes, so okay, that's again a form of unidentifiability, and here there could be multiple constraints that are equivalent in terms of disabling certain paths, and here we just wouldn't have a way of distinguishing them. So we're just going to say that these are equally good. Yeah, good with that. Or equally bad, yes. Yeah, okay. All right, so now the technique that I'm going to describe is going to work with soft constraints. So here, just to make clear the notion of soft constraints, so in fact, the type of constraints we're going to consider, there are constraints like this, where we have an expectation with respect to the cost of some trajectory, and then this is bounded by some threshold. Okay, so here, if I say that the expected cost should be less than or equal to 3, and let's say I've got 3 trajectories that each have cost 2, 3, and 4, then in this case, you can see that the average is 3, which is matching the bound, and that would be considered just fine, okay? But if you look carefully, the third trajectory has a cost of 4, then that trajectory, in fact, you could think of it as like violating the constraint, but from the perspective of a bound and an expectation, it's not violating, and then in this framework, it's fine. The alternative would be to consider hard constraints, where for each and single trajectory alone, we would like to make sure that the cost is below the threshold, and then in that case, you see, because the third trajectory has a cost of 4, then the constraint would be violated. So that's the distinction. And then so in this work, I'm going to consider soft constraints for the reason that I explained earlier, that when you work with real data, you cannot assume that your experts are perfect, and some of them are going to violate their own constraints invariably eventually, right? So that's why we have to work with soft constraints, and this is one type of soft constraints that's using the expectation. Okay, and now the next question is, how are we going to represent the constraint? So if we want to be general, I guess an idea is just use a neural network. So here, this is in fact the architecture we're going to use. So there's going to be an input layer that essentially takes as input the features of the states and actions, and then 2 hidden layers that will produce an output, and the output you can interpret it as a notion of cost that we add up over the entire trajectory. Any questions about this? Yeah.
You seem to make an assumption that the constraints need to be Markov. Is that something that you are like is true for driving?
Yeah, so, okay, this is indeed an assumption we're making that the constraints can be decomposed into terms that are per time step. And then, so as a result, yeah, then we can say that they're Markovian. Generally speaking, yeah, that is not clear whether it always holds. For a lot of problems, it does, and it's in the same way that we would often have a reward function that also just depends on state and action pair. Okay, but then if it needed to depend on other things, you could always just amend your state representation. So there are various ways of handling this, but that's a good observation. All right, so here's the algorithm that my students developed, and it works by essentially alternating between two optimization problems. So the first one, the top optimization problem, is just what we call forward control, in the sense that we take as input a constraint and an objective in terms of a reward function, and then we simply optimize that to obtain a policy. So you see this first optimization problem is just figuring out a good optimal policy given a constraint and a reward function. So you see here J pi of R is the expected reward, so that's what we're maximizing. J pi C is expected cost, and that's what we're bounding with a threshold beta. Okay, so once we obtain an optimal policy, then we go to the second optimization problem, and this one is the one that will adjust constraints. Okay, and the intuition is that if I find a policy that leads to trajectories that are different from the expert trajectories, then there's a problem, and if the trajectories of my optimal policy earn more rewards than those of the expert, then it must be that there was really a constraint that should disable or make infeasible those trajectories. So I guess this optimization problem is essentially saying I'm gonna try to make all of those policies that I came up with in the first optimization problem as infeasible as possible. So I'm gonna crank up their cost, okay, while making sure that the expert policy remains feasible according to the constraint. Yeah.
So this seems to make an assumption on the world that you can play an unsafe policy to collect data. So one thing I'm missing is that in the top part, when you have under-specified constraint, then your policy will go in unsafe places.
That's right. So it will go into unsafe places, but this is all in terms of planning, right? So these optimization problems here, there's no interaction with the environment per se. Okay, so we're more like in an offline setting where we got some data in terms of expert trajectories that's been collected, and now based on this, now let's optimize a policy as in offline reinforcement learning. Okay.
But as soon as you go into an unsafe space, you have no idea what the transitions are from data, right? Because you've never observed it.
Yeah. So this is where either we suffer from the same problems as like all the techniques for offline RL, where once you go into regions that have not been explored, you really are at the mercy of your model, and it may just be really wrong, or otherwise you have to have a simulator, or otherwise go back online and try things out. But then you're absolutely right that then that might lead to catastrophic states, and that might violate the constraints you're in fact trying to elicit in the first place. Yeah. Okay. All right, so this alternation between those two optimization problems, in our paper, we were able to prove a theorem that essentially shows that in the limit, this will converge to a policy pi star, and this policy pi star will be equivalent to the expert policy. So either it will be the same, or it will be equivalent in the sense of producing identical trajectories. Okay. Yeah, and the intuition is that if it finds a policy pi star that in the top optimization problem that does not match this expert policy, then in the second step, we're going to penalize that, and then we're going to find yet another policy at the next step. So it's just going to keep on going. That's the intuition.
Yeah, so it might be the same question I already asked, but is it somewhat equivalent to say that you add a negative reward to states you don't observe in your trajectory and kind of like merge that with the normal reward and then you also get that policy?
Yes, and also, okay, we're not updating the reward function. So in this setup, as I explained at the beginning, we assume that we know the reward function, it's fixed, and that's it. All we're updating here is are the constraints. So we're updating the constraint function. So in other words, a cost function, and then we're going to use it to penalize more those states that are visited by the policy we just found, but are not visited by essentially the expert policy.
I have the same question. What's the difference between a soft constraint and a reward, a negative reward?
Yeah, that was true.
Well, okay, so yeah, these are great questions. Okay, so if we look at the theory of constraint Markov decision processes, okay, so there the optimal policy is not necessarily deterministic. There are constraint Markov decision problems where the optimal policy is necessarily stochastic. So from a mathematical perspective, it is tempting to just say, oh, the constraint, why can't I just use the Lagrange multiplier trig, move it into my objective, interpret it as a reward, and so on. If you do this, then it looks all great. You obtain an optimal policy after that that's going to be deterministic, but that may not match at all what you would have found by just keeping things as constraints. Okay, so I guess the bottom line is that the space of solutions for constrained Markov decision processes is a space of stochastic policies in general, whereas for unconstrained Markov decision processes, then the space of optimal policies can be restricted to just deterministic policies. Okay, so there's a mismatch between those two. At least this is usually the easiest way to see that these things are not mathematically equivalent. Yeah. Okay. All right, so these two optimization problems are fine on paper, but to implement this in practice, it's not easy. And it's the second one here that has a maximum optimization that tends to be harder to optimize. So my student who implemented this came up with an approximation, and then the idea is that he replaced the inner minimization over the space of optimal policies that were found by a mixture policy. And here the mixture, the idea is that we're going to combine all the policies in the set capital Pi here into a single policy just by randomizing between them, okay? And with this, the approach now is much simpler to implement, but we lose the guarantees. So we don't have any theorem that this would necessarily converge, but in practice, it tends to work well. So that's what we did. Any questions about this? Good. Okay. All right, let me show you now some experiments in robotics and also with respect to highway driving. Okay, so for robotics, we took three common benchmarks, half cheetah, ant, and cart pole, and then we added some constraints. So here we created synthetic constraints to essentially induce problems where we could verify what happens with our approach. And the benefit is that because we created those constraints ourselves, then we can compare the constraints that are recovered to the true underlying constraint. So the first column here corresponds to the synthetic constraint that we created. So here, when I say creating a constraint, it's really creating the cost function that goes into the definition of the constraint. And the idea is that for half cheetah, we simply impose a cost where we said the cheetah is going to incur a cost of 1 whenever it goes backward. We'd like it to essentially just walk forward. And then for ant, same thing, it should only walk in the positive direction along the x-axis. And then for the cart pole problem, we said, okay, we'd like it to remain within a bounded region. So I shouldn't go too far on the left, shouldn't go too far on the right. And that led to a cost function that looks like this, okay? Then we tried our algorithm, and these are the cost functions that were recovered. So you can see that they are matching, at least in terms of shape, the original true cost function. And then in the middle, we've got some baselines, previous algorithms that were not always working well, and then in some cases just did not recover at all the constraint function. Okay, so this gives you an idea for those robotics problem. Now, more interesting is we did this for autonomous driving. We took the HAIDI data set. So HAIDI data set is a data set that was recorded by a German company where they had a drone essentially record cars passing on a German highway for some period of time. And then, so we have the XY location of every car, the shape and size of the car. We also have the velocity, acceleration, longitudinally as well as laterally. Okay, so we have all that information, also where the lanes are, where the boundaries of the road are, and so on. And then we learned two types of constraints. So in this first figure here, we're learning essentially a constraint about the gap to the car in front. So we'd like to understand like how big of a gap somebody should leave based on how humans drive. And this would often depend on the speed, right? So intuitively, if you drive faster, you tend to leave a bigger gap. If you drive slower, you tend to leave a smaller gap. And what we can see is in red, these are the expert trajectories. So human drivers, these were essentially what they did in terms of their speed, velocity, versus the gap. So that's the center to center distance of the cars. And yeah, so they all cluster around here. And now, if you look at, I guess the right side of each plot, there's a gray scale here that indicates that at zero, there would be, when it's zero, that means there's no cost, and that's the black region. So the black region would be considered no cost, and then white means that there's a cost of one, okay? So in general, you see, we would like the expert trajectories to be in the region where there's no cost, because that would mean they're going to be feasible. And then otherwise, we have to disable some other region, and that's what we observe here. So our technique produced this plot. These are the other two alternatives. And then what's nice is that you see it found a decision boundary here for the cost function that increases with the speed. And that makes sense that naturally people tend to leave a bigger gap if they go faster. We did the same thing with lane change. This time we're looking at the lateral velocity as well as the distance to a car in the next lane. And again, we've got in red the human trajectories. Now, when you do a lane change, you can change lane on the right or on the left. So that's why there's like two blobs of trajectories. So the first blob here is changing lane on one side, and then the second blob is changing lane on the other side. Okay, these things are symmetric. And then our approach essentially found again that the expert trajectories, there's no cost, and then outside of that, there is some cost, and then this one just didn't work at all, and this one didn't do something very good either. Okay. So that's, okay, any questions regarding this? Yeah.
So how do you interpret the constraint? Like I'm trying to figure out like if you fitted a cost specifically for this one action, like you have episodes of lane changes and that's it, or is it like you have like one part of many constraints?
Okay, so I guess what we did is we took the data, extracted scenarios where there was a lane change, and also scenarios where there's a car that's driving besides another car before it does a lane change, so that effectively there's a car blocking, right? And then we learned with that, and then after that, we took some other part of the data set and also tested to see what happens. Yeah.
So is it a cost that takes only like it takes the whole state space or just the data set?
So, okay, yeah, here we we tried at the beginning to just feed everything in because, neural nets are powerful and, they should just be able to handle it. But obviously, there's an inductive bias, and here we do not have like a lot of data. We have some amount of data. I believe this data set, so XZD and HID, these are the two data sets, they have on the order of like, I think maybe 50 to 100 files. In each file, there's a recording of what happens on the highway for some amount of time that could be maybe on the order of 1 or 2 hours. And then so it's actually not that much data. So we ended up having to like restrict the features to just those that we knew would matter, okay? We did try with just feeding in everything, but it just wasn't learning fast enough with that.
In each square, the bottom right corner is okay and the bottom left corner is not. So why is that? So why is it okay? You haven't got any data for either of those.
Yeah.
Somehow that's part of your model.
Yes, so, okay, so here, I guess this would mean that the lateral velocity is higher.
Give me some lane change.
Yeah, so that would mean a southern lane change. And in terms of the distance, so here there would be a bigger distance. So, okay, so here this sign distance is essentially the distance to your target lane, and we're looking at the lateral distance. So, I guess it did not have any data here. It did not infer any constraint, in large part because when you're starting at a certain distance, you see, if you're just starting from the adjacent lane, then you've got a distance of roughly 5 meters, so that's why there's nothing beyond that. And then if you have as a goal to change lane, you're just gonna go towards 0 to reach your target lane. And then it's really only, I guess, in this region that we would have data. And then to go in the opposite direction, would essentially just earn less reward. So that would be suboptimal, and therefore there's no reason for us to have a constraint that would disable that, because anyway the agent would never do that. So that's the reasoning. So, but here, I mean, you're raising a good question that I guess this part, it could be, I mean, it wouldn't hurt to have a constraint, at least in those scenarios, but the way the algorithm works is that it would not impose a constraint unless that would lead to some trajectory that would earn higher reward, but those trajectories will earn lower rewards. All right, so when we did this, our industry partner was pleased, but at the same time was a little uncomfortable with our notion of expected constraint and what is something a little more interpretable. And then, so we ended up looking at another framework known as the maximum entropy framework that is quite popular in reinforcement learning, also as inverse reinforcement learning. And the way this works is that if you have, let's say, rewards for some trajectory, then the probability that you would follow a trajectory would simply be proportional to the exponential of the reward. And the idea is that you see, the more rewards can be earned, then you're more likely to follow this trajectory, and it's very intuitive. Now, this framework has been extended to the case with constraints, and here the idea is that now the probability of following a trajectory would be proportional again to the exponential of the rewards times another factor that would be the probability that the constraint would be satisfied. So here, C tau would not be a cost per se, but this would be interpreted as a probability that some underlying constraint is satisfied. Okay, and then you can have something similar where now your policy is just going to be of this form. Okay, so then using this framework, we can obtain an algorithm that is also simpler, where we have a single optimization problem instead of 2 optimization problems. So we can define a loss function that essentially tries to optimize the parameter theta of our constraint function here in such a way where we would maximize the likelihood that the expert trajectories have the highest score, okay, or have the highest probability of being executed. Okay, so you see this term here, the log of this ratio is essentially the log probability of each trajectory. And then if we optimize theta in such a way where the trajectories of the expert end up having the highest probability, then that would mean that perhaps we now have some constraint function that ends up disabling otherwise all the other trajectories. Now, working with this is fine in theory. In practice, we've got a problem where the denominator has this exponential sum over all the trajectories. Okay, there's too many trajectories, obviously, that one could consider. And then, so we came up with a very simple approximation where we replace this large sum by the sum of the best trajectories found by a beam search algorithm. Okay, so the idea is that we don't need to worry about the trajectories that are bad. We just want to consider the best ones and make sure that among the best ones, we're going to have the expert trajectories. So we use beam search to find some estimate of the best trajectories. And then we would like the probability of the expert trajectories to be with the highest score among these best ones. Okay. So when we did this, then we arrived at I guess probabilities for the constraints. So the longitudinal constraint is here, lateral constraint is here. So it's similar to what we saw before, but now it's not a cost function, but instead it's a probability of the constraint being satisfied. And our industry partner was very pleased by this because that was more directly interpretable for them. And then the next question they ask us is, well, can you take those constraints now, drop them into a simulator, and then just drive a car with this? Like, would your car just drive safely or not? And then so we tried this, and it led to the following animation. So here we took some trajectories from the CAIDA and XCD data set. So the idea is that every blue rectangle is essentially a car on a German highway that was recorded by a drone. And here I'm simply using Matplotlib to render, I guess, the motion of those cars. And then we took one car that's in green, and then we said, okay, now we're going to control this car, and then we're going to give it as a goal to reach the end of the track as quickly as possible. So that's its reward, to drive as quickly as possible, yeah? But satisfy the constraints that have been learned with the approach that I demonstrated before. So now what we see in the red, so the red rectangles that are around the green are essentially like the gap, the longitudinal gap and the lateral gap that it tries to satisfy, because it considers having cars inside that gap to be unsafe. And then so you notice that you see it will never have any blue car overlapping with those red rectangles, because these are sort of like the safety boundaries that it tries to maintain. And then after this, in terms of driving the car with this, then we just apply beam search again. So find some trajectory that will reach the end as quickly as possible. And naturally, it will change lane when it's blocked by a car in front, and it finds that there's a way around the car that's safe. It will do that. And so that's what we observe here. And if you look carefully as well, you see when it's blocked by another car, then the red rectangle in front tends to be short because it's driving slowly, and then if the speed is low, then it can essentially keep a small distance. But the minute that it doesn't have a car in front, then it can accelerate, and then you see this red rectangle increase, because now it will try to keep a bigger distance to the car in front. Okay, so this is all happening naturally, and again, those rectangles, the red rectangles correspond here to the constraints that were learned with the previous approach. Any questions about this? Yeah.
Why does it word of constraint behind? Like, people just like cut everyone.
Yeah, that's just because when we did the training here, we extracted from the data scenarios where there were cars in front or car on the side, but ignored completely cars behind. So we just didn't expose it to that type of data. Otherwise, they would have learned something about this. And indeed, there are situations where it looks like it's like literally cutting off somebody. Yeah, so that part may not be entirely safe. Yeah. Okay, so I guess it's 10:44. I was told that at 10:50 we have to stop. I do have a second part, but I think in the interest of time, I'm gonna
You always
skip
move
this.
next door to do questions.
Sorry, yeah.
You always finish here and then move next door to do questions.
Okay, so I guess we can go next door for that. I guess what I'll do now is I'll simply conclude, and I'll just skip the second part because it would take a bit of time. And let me just mention that what's exciting in my lab right now is that we are developing a reinforcement learning foundation model. And then next month, actually in April, with the Vector Institute, we're going to run a bootcamp primer with several companies. We've got 5 companies that have expressed interest so far, and they've signed up for the bootcamp. And then they will effectively be evaluating our reinforcement learning foundation model for this. So what are we doing exactly here? So we're essentially trying to train a fairly large model, so it's pre-trained, to make decisions with respect to all sorts of interesting business problems. And you can see those companies, you can guess that their use cases are not, video games. They don't care about video games, and they're not doing robotics. They're not doing NLP either. Okay, so they're interested in more things like how to do marketing optimization, troubleshooting, operations research, price management, these sorts of problems. So I guess, yeah, the foundation model that we're developing is going to generalize across these types of problems. And then the challenge is really like, how can you take maybe different use cases that would be, let's say, in the context of an airline, or in the context of a bank, or in the context of a grocery store, and map this into the same space so that the same decision-making engine can serve these different use cases. So that's what we're working on. And then in a few months, I hope to be able to report on this. Okay, let me stop here.
Thanks to Pascal's excellent time management skills, we have time for lots of questions, actually. Obviously, thanks to David's excellent organizational skills, we have time for even more in the other room.
Yeah, just any thoughts on the scalability of the constraint-based approach? Because you can have constraints that are functional, all attributes of the state, and then all attributes of the action space, and then you can cross whatever. Like it just doesn't kind of explode where you could apply the constraints and what they're a function of.
Yeah, so obviously here, if the constraints are complex, then you need more data, you're gonna need neural networks that have perhaps more capacity, or otherwise perhaps that have an architecture that is better aligned with the type of constraint. And all these things matter. So here, in our case, I think we had a certain amount of luck in a sense that the constraints were still relatively simple, and then with just fully connected networks, 2 hidden layers, it worked. But I was in fact quite worried when we started that we would have to spend a lot of time figuring out good architectures, playing with these things.
Yeah, sure. Yeah. And the follow-up question is, so we had this iterative approach between optimizing the policy and optimizing the constraints. So, but for the optimizing the constraints part, I'm still not quite clear on how it deals with the possible ambiguity or underdeterminedness of where you put the constraints, right? So in your original world example, that wall could have been, you could have had a wall anywhere in some vertical range, and it would have equally. So it would have been equally suitable, and so how does your particular actual implementation deal with that?
Yeah. Okay. So that is indeed like the main source of unidentifiability. Okay. So if we look at this optimization problem here, when it does the constraint adjustment, it's in a way where it tries to penalize the policies that were found by the other step. Okay, and here you see it's an optimization problem. So there's 2 different ways of penalizing, but they would lead to the same amount of penalty for both, then it doesn't have a way of choosing and it will not care between the two. And then so as a result here, we're not claiming that we're necessarily converging to the same underlying constraint, but we're claiming that in fact this will simply converge once we find some constraint that will force the optimal policy to be equivalent to the expert policy. So that's why, like, yeah, there's no guarantee here that it's the same constraint, and your example is a very good example for that.
By iteratively adding high stars as like policy set, do you end up in like sort of a continual learning type framework here where you might forget constraints over time as you're optimizing this?
Okay, so in this version, no, simply because we keep on adding the policies to the set, and then here there's a minimization with respect to the set. So essentially, we're trying to make all of those policies become infeasible as much as possible, right? And so yeah, from that perspective, we're not forgetting any of them, but computationally, it might make sense to at some point just forget some of them, okay? But the optimization, or at least the version that we implemented here, was not doing this, it was in fact combining these different policies. So there, I would think that this would have a bigger effect. And now there's a risk that when we combine all of those policies into a mixture, that maybe there is one policy that now is part of a mixture, you know, because it's just being utilized once in a while, but that isn't sufficient to, I guess, completely disable it or make it infeasible according to the constraint. And then as a result, we might have a problem that the next time step here, they could find that policy again, right? So yeah, this would definitely happen.
Wondering, is there like a, so if the assumption is that you have access to the reward and you have some set of expert data and you're basically determining the constraint using the set of expert data that you have access to, is there any reason not to just say, have a constraint defined by some divergence between the expert data and the learned expert, and then maximize reward subject to that constraint?
So say that again. So at the end, you said that maximize the divergence between.
Why not maximize the reward subject to a divergence between the expert's policy and the data, I guess, generated by the expert and your current policy?
Yeah, so that's yeah, we could also approach it this way, where ultimately we could say that yeah, this will simply find a policy that's equivalent to the expert policy, and that's why like we just want to have a match at that level. And then otherwise maximize the rewards, right? So we could look at it this way. And in fact, if we were more like in an imitation learning framework and we didn't care about trying to recover what is the underlying constraint, then we could simply just try to do exactly what you did.
Okay. I think if there are many questions, we should take in the other room after we all grab some food and
Yes,
move
please.
there. Thank you very much.